Okay, good afternoon. It's Dr. Jensen here. Today we're going to talk about a few quantum mechanics problems. So usually in general chemistry, quantum mechanics, there are generally three different kinds of problems generally that we look at. First one being quantum numbers. Okay, we have quantum numbers, we have electron configuration, and energy diagrams. Okay, so these generally are three different ways of representing the same kind of information. All right, so let's look at a couple of different problems here. Okay, the first one we're going to look at are some energy diagrams. Okay, so usually, if we pick so usually there are two different ways that these are depicted. The first being if we are given an element. Okay, so let's say neon, right? And we want to know what is its energy diagram that goes with it. Okay, so instead of writing the whole energy diagram, usually what you'll see is just the highest level of the energy diagram. In this case, neon is in the second energy level, so you'll see 2s and 2p as its highest energy level, right? So obviously the 1s is present, right? So if you do the full electron configuration, which we can do second after this, or let's start with that instead, okay? So neon's electron configuration would be 1s2, 2s2, 2p6, okay? So again, we're reading the periodic table top to bottom or left to right. So in the first energy level, there are only 2 electrons, it's hydrogen and helium. Then in lithium, beryllium, and then the 2p starts boron over to neon, okay? So when we do the energy diagram, so it's 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3. Right, now, the up arrows are all drawn first because they're electrons, and so they don't want to pair up unless there's no more room. So after they've done the positive spin, then they will begin to pair up. And then we end up with the 2p6. Okay. If you were doing the quantum numbers for this, again, the last one added is the electron pertaining to neon. Also which orbital shelf it's on. So if we were going to do the quantum numbers, okay, this is in the second energy level, okay, from here, okay. The p orbital is the L value. So the p orbital has an L value of 1. It is in the positive 1 orientation as I've written it, and it is the negative 1/2 spin. Okay, so these would be the 3 representations of neon from this different quantum number. Okay, if we're going to look at a second question here. Okay, let's look at titanium. Okay, so titanium is a transition metal element. It is in the 3D, right? So if you look at the 3D, the transition metals, and you count over from the transition metals, it would be the second one. So it's electron configuration, 1s2, okay, hydrogen and helium, so always starts at the top, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So here's where you have to take into account that as you read the periodic table from left to right, this change is just something you have to take into account. Okay, so technically speaking, the scandium that begins the transition metals are in the 3rd energy level. They're not in the 4th energy level as they appear to be written on the periodic table. So as we read across the elements, you just have to take into account that there's this jump where it lowers down into the 3D and then goes back up into the 4s, okay, after you hit zinc, all right? So if we were doing the energy diagram, okay, so you have 4s and 3D, right? So it'd be 4s1, 4s2, 3d1, 3d2. Okay. Again, that's just representing the highest energy levels. Okay. Now, if we were doing the quantum numbers for this, again, the last electron added would be the one we were interested in. Right? D, the L value of D is 2. Okay. All right. So if we represent our different orbital shells by what is the M sub L ranges from negative L to positive L, right? Which, so in this case, from 2 is negative 2, negative 1, 0, positive 1, and positive 2. Okay. So this is in the 3rd energy level. It is in the d orbital, which has an L value of 2. It's located in the negative 1 shelf, and it is a positive 1/2 electron. Okay, so this would be the electron configuration, the energy diagram, and the quantum numbers for titanium. Okay. Now, if we look at, let's see if there's another example here. All right, so commonly when we're looking at quantum numbers, one of the other kinds of questions for quantum numbers is whether or not something is allowed or not. And so oftentimes you will get things like, you know, it leaves off, so sometimes they'll leave off the last value. But the first 3 have to be given. And so this is the N, the L, the M sub L, and then the M sub S. Right? All right, so the question here is which one of these is not allowed, okay? Or if we're looking for whether or not it's allowed or not, right? So the rule here was usually your M sub S is where you would want to start, but since it's not given, it kind of eliminates that down. But the M sub S only has a positive 1/2 or a negative 1/2 value, okay? Those are the only 2 possibilities for the M sub S, right? But since we don't have to worry about that, right? M ranges from 1, currently the energy levels of the periodic table range from 1 to 7 currently. So 1 to 7, so, but it's any positive integer, okay? So all of these are fine, okay? The L value ranges from 0 to n minus 1, okay? So the L value is n minus, up to n minus 1, which means it can be 0, but it can't be greater than the n value. All right, so we're looking for L values that are less than n. So 1 is less than n, or 1 is less than 2. 2 is less than 3. All right, so right here, 3 is not less than 3, obviously. 3 is less than 4, so that one's fine. Okay, so this one here would not be allowed because of that rule. As soon as one of them is not allowed, the whole thing is not allowed. So now it's just a matter of whether, is there another one that's not allowed or not? So the M sub L value ranges from negative L to positive L, okay? So it can be anything within, it just can't be greater than, can't be greater than the L value, okay? So negative 1 is within that range, 0 is fine, okay? 2, again, it doesn't really matter. We've already eliminated that one. And 0 is, again, fine for a value of 3. Okay, so we'd say this one here is not allowed because the L value cannot be greater than or equal to the N value. All right. Again, some variety of quantum numbers and things. If you're given a quantum number, let's say another way to look at these questions would be, given a quantum number, what element is this? Okay, so you want to go right to the last one. Okay, so we're in the 3D9. Okay, 3D9. So we're in the third energy level of the D orbital, which is really the first part of the transition metals. That's your scandium to zinc area. Okay, so if you're in your periodic table, okay, here's your S, your P, and your D, right? So your 3D starts right here, okay? So it's the first row of D, all right? Here's your 4S right there, and then your 4P would continue over here, right? So 3D is that first row of transition elements, and so then we count over, starting from scandium at 1 over 9 places, and then we would find the 3D9 is copper. Okay. Now, one thing you got to look for when you have problems with these various electron configurations is dealing with where they give you a variety of electron configurations. So if we were looking for, if they gave us copper and a multiple choice of which one was the right one for the electron configuration, what you would look for is other variations. All right. So if we had two choices here, right, both of them end in 3D9. So the last one is where you start. That helps you to narrow down your choices. But if both of these are 3D9, they both be representing copper. So the question is then, which one is drawn right? And so what you'll often see are errors in the code, in the electron configuration code as it's written, right? So we have to know, for example, the s orbital can only have 2 electrons. Okay, the p orbital can have 6 electrons. The d orbital can have 10 electrons. Okay, so what you are going to be looking for is errors where they either exceed the number or it's not enough. Like they'll get over to like, they'll write it like this as well. Sorry. Okay, so you have, everything, the last one again is looks like it's right. 1s2, 2s2, 2p6, 3s2, 3p4. And so it's not enough before they went on to the other part. So we just have to watch for the way it's written. Okay, so you have to watch for that the S, P, and D should have the proper number of electrons if it's filled up. Okay, now if it hits stopped, obviously the 3D9 is fine because that's where it's stopping. Okay, it can have up to 10, but if we're trying to represent something along the way, then it's going to stop here, but the rest of these are going to be filled. Okay, at least at the general chemistry level, we use what are called ground state configurations, so there shouldn't be variations in the electrons. All right, so that is it for this video on quantum mechanics problems for general chemistry.